Okay, let's take a look at the Smith chart. And specifically, we can look at the Smith chart using a program here, so we can add some components and see what they do and get the calculations done for us. When we look at the Smith chart, it's often difficult to remember which side is the short and which side is the open, particularly if you don't use the Smith chart all the time. But a trick that you can remember, the Smith chart is confusing because it's all these circles looped on top of each other, but at the center is this horizontal axis. And that axis represents all of the purely resistive terminations that you encounter. And just like a Cartesian system, it goes from 0 on the left to infinity on the right. And in terms of terminations, a zero impedance termination is a short. So the short is always going to be on the left. And I will have to keep my left and right straightened out. That's maybe one of the also an important thing to keep in general, your left and your right. Same goes for counterclockwise and clockwise, by the way. So on the left, we have a short, and the terminations increase. They go at the center of the chart. We have the characteristic impedance of our system. When we normalize the Smith chart, we take all of these resistances and divide them by the resistance that we want to normalize to. So for example, most commonly 50 ohms is used as a system characteristic impedance. So a Smith chart will then be normalized to 50 ohms. That is, all the impedances are then divided by 50, and you end up with a value of 1 at the center of the chart. This was done as a convention or a convenience in the early days because that way you could just print one kind of chart that's normalized and use it for any type of terminations. If you were using 75 ohms and working in the cable industry, you could still use this normalized chart, not have to have a separate stack of charts for each impedance. That convention has carried over to modern times, so even the computerized charts are displayed as normalized on your test instruments and so forth. And that's just something that we're used to seeing. Another benefit of normalizing is that you can scale the chart to a different impedance temporarily. For example, when you work close to the edge of the chart here on the left or the right, it starts to get really jumpy and sensitive to small changes. If instead you normalize the chart to a higher or lower impedance, depending which edge you're at, then those impedances get spread out and it becomes easier to work at those other edges of the chart. So there's still a modern application for normalizing the chart. Let's look at some of the significant observations we can make on the Smith chart, and particularly with respect to working at higher frequencies. If you're working with a circuit and you wish to connect a component to ground, you're going to expect that what the component sees is a short to ground. You're going to expect the component to see a termination way over here on the short circuit side of the chart. But what the Smith chart allows us to do is see what happens when we have a length of line between the component and the ground, which is physically what you end up with in most circumstances. You don't just have the component, the output of the component just tacked onto the ground. In the case of microelectronic circuits, you've got a via or some other trace between the component and ground. And then in other applications, you might actually have a physical length of line. And on the Smith chart, we can represent that by just adding a series transmission line, which we have available in the program here. Adding a transmission line ahead of the component has the effect of shifting the phase of the termination. And the phase shift is proportional to the electrical length of the transmission line. And that's why it's handy to represent electrical length in terms of degrees of phase shift. On the Smith chart, since we're looking at reflections, the phase shift is actually going to be double the electrical length of the line, because the phase gets shifted one time traveling down the line, and then that same amount again reflecting back. So there's 2 times the phase shift. The phase shift is 2 times the electrical length of the line. So if we add a length of line ahead of the short that is, say, 45 degrees long in terms of electrical length, then it's going to shift the phase of the termination by 90 degrees. And we can see the electrical length being represented calculated here by the program, and it's showing up here as 45 degrees. Now, if you go back and calculate the physical length of the line with respect to our current frequency is 500 megahertz. So the physical length of the line can be calculated using the formulas for electrical length based on frequency. And it's also going to depend on the length of the wavelength, the dielectric constant, because the dielectric constant has the effect of shortening a wavelength in a line. So this is all for a transmission line that it has a dielectric constant of 1, or the same as air. But those can be adjusted using the formulas as well. Now, if we increase the length to the point where we have a quarter wavelength long, or 90 degrees, then in the reflection area, we're going to see a 180 degree shift. And since we're on the edge of the chart, you'll notice this Q value kind of dipping down. That's a rounding error. Really, the Q should remain kind of on the edge of the chart here. It's sort of infinite. But I didn't quite tag the edge of the chart. And then also the math can tend to blow up on the edges here too, because of divide by 0 and things like that. So really the Q on the very edge of the chart might start not making 100% sense. But the key takeaway here is that if I get to a 90 degree length, then what we'll see is a 180 degree phase shift on the chart. And so our component now, instead of seeing a short, because of this length of line in between there, it's going to see an open termination. So our performance is going to be tied to as if the component was seeing an open circuit, which is not at all what we would be expecting. So it's important to be able to predict when this would happen and adjust our circuit accordingly, either by adding more. You could add even more transmission line until you got up to a half wavelength, which when you double that becomes a full rotation of 360 degrees. That brings you back to the short. So a half wavelength just brings you right back to where you started from. I can show that half wavelength phenomenon occurs anywhere on the chart. I'll bring it just about close enough to where it's just about not exactly on top. That's going to let me click on the original termination. But it should be that anywhere I move this termination on the chart, that length of line in between there is going to bring the termination right back around to the original starting point, because I've got a half wavelength long transmission line between the termination and the point where I'm looking at the impedance, the end of the line. And again, if I change that back to 90 degrees, we're going to get a 180 degree phase shift. So the other thing that can happen is that if you were on the upper half of the chart and expecting for your component to see a inductive termination, if you have a quarter wavelength line, now you're suddenly going to see instead you're going to see a capacitive termination. And that can have implications in amplifier design or other specific applications where you're anticipating a very performance based on a specific termination being presented to the device. So another useful feature of the transmission line, a series transmission line, that we saw from the formulas is that you can use a quarter wavelength line to do impedance matching. And so let's say we had impedance of 10 ohms, which is normalized to 0.2, and we wanted to match that to 50 ohms, which normalizes to 1. You can see that a quarter wavelength line brings the termination over back to the horizontal axis again, but in this case it's at the wrong place. But if we adjust the impedance of that line according to the formula for the input impedance of a transmission line, we saw that the input impedance is affected by the characteristic impedance of the line that we insert. So if we happen to know that if we make that characteristic impedance the same as the square root of the product of these two terminations, we'll get an impedance match going on. And so the square root of the product turns out to be, let me get this transmission line clicked here. If we set this to 22.3, I believe, that's going to shift that termination to a matched termination. So that's a quarter wavelength matching section. All right, and last but not least, let's just look at terminations on the Smith chart briefly here. We can see that the for any sort of passive component like a capacitor or resistor or some combination of those two, the reflection coming back is going to at most be equal to the transmitted forward wave in magnitude. It's not going to be able to add energy because it's a passive component. But once you start working with amplifiers, transistors basically, and you're trying to build an amplifier, it's possible that the reflected wave could, not desirable, but it's possible that the reflected wave could come back stronger than the forward wave. And in those cases, it's actually going to send the magnitude to be greater than 1. It's going to leave the chart. And in those cases, it's not a stable, electrically stable situation, because if the reflected wave adds in phase with the forward wave, then it's just going to keep getting bigger and bigger and bigger. And you're going to end up with an oscillator. And sometimes you might be wanting to build an oscillator, and that's fine. But if you're building an amplifier, you don't want to build an oscillator. So you can use the Smith chart in those cases as a design tool to avoid oscillations. And that gets into a more advanced applications of the Smith chart, where you can actually predict where oscillations will occur using something called stability circles. And those are going to be based on measurements of the transistor itself. S-parameter measurements of the transistor will let you predict regions of stability on the Smith chart, where if you provide the transistor with the wrong termination at one end or the other, it's going to oscillate. And that can be predicted on the Smith chart graphically using S parameters. One more thing we can look at on the Smith chart is the concept of Q. And the Q value is really just the ratio of the real or resistive portion of the termination to the reactive or imaginary portion of the termination. And in general, the higher that ratio, or the more reactive the component termination is, in general, the narrower the bandwidth the circuit will have, or the more sensitive to changes in frequency the circuit will be. So, and one observation we can make is that the closer we get to the edges of the chart, or the further away from the horizontal axis, the higher the Q values become. So notice the Q value, if I'm close to the horizontal axis, the Q goes from 0, and I can either go straight up and the Q value will increase, but the closer I get to the edge of the chart, the higher it starts soaring away. And the same goes for left and right edges. And also, in very practical terms, the software starts to become very susceptible or sensitive to rounding errors as a result as well. So the Q value goes way up. And we can demonstrate that as a result, the matching networks become much more sensitive to changes either in frequency or shifts in, if you get the component values off a little bit. Let me build a simple matching network from this point that's really close to the edge of the chart. I'll build a simple matching network. Looks like from here I can go, well, we can already see how difficult it is because I need to go up just a tiny bit on the red to get to from this green circle to this green circle that goes to the center. It all becomes very hard and difficult to see. So let's see, I need to add a tiny bit of upward on red. So a tiny bit of inductive series inductor, and then a great deal of down on green. So let's see. So you can see I'm going to have a real difficult time, just pixel by pixel is going to really change the matching network working close to the edge there. It just gets really tricky. And that's because the Q is high. Okay, so there I've built a matching network. Now if I look at this same matching network, adding a new frequency, say 525 megahertz, you can see that that matching network is really sensitive to changes in frequency, because here's the same matching network at 525, and it's now it's, instead of being perfectly matched, it's got a gamma of 0.3. So not nearly as good, whereas at the original frequency. So it's more frequency dependent, but also if this inductor value changes a little bit, say it's a 10% inductor, and let me get rid of that second. Let's look at just the component values. So here's the inductor. I'll select it. So we're pretty well matched, but now if I change the inductor, I had a 0.5 nanohenry, which is, we add a little bit of inductance, and you can see if I'm off by 10%, it throws the network off quite a bit more. Whereas if I'm building a match, if I have a termination that's closer to the center, I'm going to end up using values that are easier to work with and less prone to shifting. So here I have a different termination that's closer to the horizontal axis and further away from the edge of the chart. It gets easier to build a matching network because it's not so touchy. Let me try changing this value by 10%, and it's going to throw it off too, but not nearly as much as 10% change shifted the values when I was working close to the edge of the chart. So high Q values appear towards the edge of the chart, both the left and the extreme right edges. And then in between, it's mostly as you get to the top and further away from the horizontal axis, just represents higher Q values, which means greater frequency selectivity and sensitivity. All right, so that's looking around on the Smith chart a little bit, getting a feel for where things are. And it's useful, as in most cases, most new topics, it's always useful to kind of play around with some practice examples. I personally feel like using some software just to do the calculations for you gives you the freedom to kind of move things around without getting bogged down with the tedious calculations that are going on in the background. It's definitely prudent to know the formulas and do some calculations by hand here and there, but I think it's also beneficial to have access to software and play around and sort of get a feel for the way things work that way as well. So hope the video was helpful, and we'll look forward to looking at other topics in the future.